We're looking at angle between two vectors, and this is actually an application or rearrangement of the dot product. So once we have worked out what the dot product is, or the scalar product is, we can rearrange its formula to find the angle between two vectors. We know from previous work that using the dot product, if we have vectors A and B separated by some angle theta as pictured, we dot them together by A dot B is the magnitude of vector A multiplied by the magnitude of vector B, which are both scalars, multiplied by cos theta, which is also a real number, hence a scalar, and the result is a scalar quantity. However, if we were given the dot product and given the magnitudes of each of the vectors, we could then find the angle between them. And this is what we do. So isolating cos theta first, we look at what we have to do to rearrange the equation. And that's all this is, a simple rearrangement. Well, we're dividing the right-hand side, which has been multiplied here by the magnitude of A times magnitude of B. We have to undo that multiplication with a division of the same quantities. So to isolate cos theta by itself, we have to divide by magnitude of A multiplied by magnitude of B. They are together on the denominator, and we have to do that to both sides. If we do it on the left hand side, we get what I'm writing now. So the dot product divided by the product of the two magnitudes will give us cos theta. Thus, to isolate theta, which is what we're looking for, the angle between the two vectors, we have to take the inverse cos of both sides. And if we take the inverse cos of cos, we have just theta, and on the right hand side it's the inverse cos of what we had in the previous line. And that will give us the angle in degrees between two vectors. An example we see on the right hand side, given vector u, specified there in Cartesian form, and vector v, find the angle between the vectors we call theta. First thing we need to note here in the solution is that we have Cartesian form of three-dimensional vectors. Vector v appears to be specified differently to vector u. That's because vector v doesn't have its x scalar, in other words the operator in front of the I component specified, but indeed it is there, it is 0i. So in our solution we can clarify by rewriting vector v to match the three-dimensional format of vector u, which is what I'm doing here. Now we have to recall our formula, and there it is from our previous notes. So let's do that. In this case it's the inverse cos of u dot v over the magnitude of u by the magnitude of v together. Let's see what we have. Well, we don't have the magnitude of u and the magnitude of v, but we can work them out using our previous knowledge. We don't have the value for u dot v, but we can also work that out. Crunching u dot v, from our previous work we get negative 40. Pause the video and have a look if you need to. From previous work we know that the magnitude of u will be given by that formula, so we sub in the corresponding values. We do the maths. Pause the video if you need to have a closer look. To 3 decimal places, which is what I've decided to go, we have 7.810. Substitutions for the magnitude of vector v. After crunching the numbers we get approximately 7.280. Subbing in, and on the calculator the contents of the brackets is negative 0.7035, let's say negative 0.704. So we write that in, we sub in the calculator inverse cos of that, and I get 134.7 degrees, 134 written in as such. So if you can do a question like this, that's probably at the average to above average level. It could get easier than this, and it could get more difficult than this, but this is probably a level of mastery if you could do that. So remember, the skills were to rearrange the dot product formula, calculate u dot v, calculate the magnitude of u, calculate the magnitude of v, finally sub those in and substitute correctly, and you get your solution. Time to try a few.